Hello, welcome to Maths with EJD. In this video, I'm still talking about probability with attention to central limit theorem. Okay, the central limit theorem, or CLT, is one of the most fundamental concepts in statistics. It states that the distribution of the sample mean of a large enough sample drawn from any population will approximate a normal distribution. Regardless of the population's original distribution. Provided the samples are independent and identically distributed. That is IID. Okay. So the larger the sample size, the closer the distribution of the sample size, the larger the sample size, the closer the distribution of the sample mean. Yeah. The distribution of the sample mean, the closer the distribution of the sample mean gets to normality. Okay. I mean, this bears some kind of resemblance with the law of large numbers. Okay. Mathematically, if a population has a mean mu and a standard deviation sigma, then the mean x bar of a sufficiently large random sample of size n will follow a normal distribution with mean mu and a standard error instead of standard deviation, or standard error, because we are talking about sample, so it's standard error, not standard deviation. Standard error sigma all over square root of n, as we saw under the law of large numbers. So there's a key resemblance. So the key formula the key formula is that X bar is normally distributed between mu and standard error sigma squared over n. Of course, sigma squared over n is coming from the fact that sigma over root n can be normalized to be square root of n. Okay, yeah, that's if you square that side, right? You should have the standard error squared, sorry. So that's sigma over root n squared. That's like sigma squared over n. That's why we have this now. Okay. So the formula expresses that the sample mean follows a normal distribution, with the same mean as the population mean, but with reduced error, with reduced variance. So variance, standard error, and all that. It is scaled down. It is scaled down by the sample size. Scaled down by the sample size. Okay. So that's the idea of the central limit theorem. Okay. So let's look at the importance of the central limit theorem. Importance of the central limit theorem. Okay. Number one, it is the foundation. It is the foundation for inferential statistics. Okay. So we can say that the central limit theorem enables statisticians. It enables statisticians to infer population parameters, like means and proportions, based on sample data, So this serves as the backbone of various statistical methods, such as confidence intervals, and hypothesis tests. So that's one importance of central limit theorem. Okay, let's look at another one. So we talk about normal approximation for non-normal data. Okay. So, of course, the very essence of central limit theorem tells us that the central limit theorem actually guarantees that even when the population distribution is unknown or non-normal, the distribution of the sample mean can be approximated. The distribution of the sample mean can be approximated by a normal distribution. By a normal distribution for sufficiently large sample sizes. This actually simplifies many analysis. This simplifies many analysis. Okay. All right. So, of course, very close to that is the third point, which is that it simplifies analysis of complex data. Analysis of complex data. Okay. Now, in practical applications, many populations have distributions. Many populations have distributions that are difficult to work with. This is very close to the second thing, difficult to work with. Well, the central limit theorem allows us to ignore the original complexity, when analyzing the sample mean. When analyzing the sample mean, as it tends towards normality, Okay. All right. So having said all this, so I'll just make quick snapshots of the applications. So let's talk about the applications of the central limit theorem. So we are moving on to applications of the central limit theorem. Okay, they are related to things you have mentioned before. First of all, it can be used for we can use it to construct confidence intervals. So here, the CLT allows for constructing confidence intervals for the population mean when a sample is large enough. So this means that even when the underlying data is not normally distributed, we can use normal distribution techniques to estimate population parameters. And a very good example of that is that a researcher collecting a large sample of test scores can use the CLT to estimate the average score of the entire population with a high degree of confidence, Okay, that's talking about confidence interval. Now, let's talk about hypothesis testing. So for hypothesis testing now, so the CLT justifies the use of Z-tests and T-tests for comparing sample means. It justifies the use of Z-tests and T-tests, okay, for comparing sample means to population means, or comparing two sample means, even if the data isn't normally distributed. A very good example is this, that a company might want to test if the average production time for an item has significantly changed from the historical average, of 30 minutes by analyzing a sample of recent productions, Okay. And then we have number 3, quality control. So in manufacturing, the central limit theorem is critical in quality control processes. By sampling product batches and calculating their means, factories can detect shifts in production quality. A very good example would be a factory randomly samples light bulbs to ensure they last for the expected number of hours. So if the sample mean differs, significantly from the target, it could signal production issues. Okay. Then we have another application talking about financial markets. So in finance, the central limit theorem is often applied to model returns on investments. Even if daily returns are not normally distributed, the average return over a large number of days can be modeled as normally distributed. And a very good example of that would be in Monte Carlo simulation. This is a very popular thing. Monte Carlo simulation, which model stock price movements over time. The central limit theorem enables analysts to treat the sum of returns as normal over a large number of simulations. Okay. And then we have another example talking about polls and surveys. Okay. The central limit theorem allows pollsters to draw conclusions about a population's opinion based on a sample. It is the reason why polling data, when properly sampled, can give accurate estimate of public opinion. So a very good example would be in politics, right? In political polling, a sample of voters is taken to estimate the proportion, of the population that supports a particular candidate. Even if individual opinions are not normally distributed, are not normally distributed. All right. So having said all of this, I like to conclude this topic with a worked example, which will drive all the points home. Okay, let's consider a scenario. Worked example. So let's consider that a bakery is interested in the average weight of its chocolate chip cookies, but the weight of individual but the weight of individual cookies follows an exponential distribution, with a mean of 50 grams and a standard deviation of 10 grams. So the bakery takes a random sample of 36 cookies and wants to know the probability that the sample mean will be less than 52 grams. Okay, so that's the scenario we have, that a bakery is interested in the average weight of its chocolate chip cookies, but the weight of individual cookies follows an exponential distribution. So you can see the distribution is not normal, it's exponential, with a mean of 50 grams and a standard deviation of 10 grams. Okay, so the bakery now takes a random sample of 36 cookies and wants to know the probability that the sample, so the key is the probability that the sample mean will be less than 52 grams. Those are like the key points in this scenario. So let's go step by step to solve this. So step by step solution. So number one, what do we have? Information. So given information, first of all, we have the population mean, which is 50 grams. We have the population standard deviation, which is 10 grams. Then we have what else? We have the sample size, that's 36, that's n. And then we have we need to find P such that X bar is less than 52. Okay, so we need to find this. Now this is the sample mean. This is the sample mean, because this is the population mean. This is population standard deviation. This is sample size, okay? So these are the things we have now. So what can we do with them? So the next thing we want to do is to step 2, applying the central limit theorem. That's the next thing. So so we have this. So applying the CLT now. So according to this central limit theorem, the sampling distribution of the sample mean will be approximately normal. All right, will be approximately normal. So the standard error SE, like I said, standard deviation is for the population, standard error is for the sample. So the standard error is calculated as SE, which is standard error, equals population standard deviation divided by the square root of the sample size, which is 10 for sigma all over square root of 36 sample size. That is 10 over 6, and that is 1.67. Okay, that is the standard error. So we now know that the sampling distribution of the sample mean is approximately X bar normally distributed with mean 50 and standard deviation 1.67 squared. Okay, just like what we got now. So the next thing we want to do is to standardize the problem. So that's step 3, standardizing the problem. So what that means is that we are converting to z-scores. So that's the next thing we do. So here, to find the probability, probability that X bar is less than 52. So we convert the raw score, to a z-score. So that way we standardize it. That means we have z equals 52. Of course, that's more like generally, right? That is, 50, it's mu, that's population mean, right? So basically, z-score talks about x minus mu divided by standard deviation. So that is 52 minus 50 all over 1.67. That is approximately 1.20 for the z-score. So the next thing we want to do is to find the probability for finding the probability. Okay. So in this case, we have to use a Z table. Using a Z table. Now, I always advise about tables. The tables differ. So make sure if you want to use a table, make sure you have one that you've always used in class and use the same in an exam so you don't get confused. Because if you get another table, just for example, it might just be thrown off balance because the tables can be read in different ways, although so you get the same answer. So using a Z table, the probability corresponding to a z-score of 1.20 is approximately 0.8849. Okay, So, we got a Z-score of 1.20. So the probability of corresponding to that is actually 0.8849 if you use the table, so you can check. So therefore now, probability that X bar is less than 52 is equal to 0.8849. Okay. So the interpretation of this, how do we interpret this now? Interpretation. Okay. So there is an 88.49% probability that the sample mean weight of 36 cookies will be less than 52 grams. This is possible because despite the individual cookie weights following an exponential distribution, the central limit theorem ensures that the sample mean follows a normal distribution, due to the large sample size. Okay. So in conclusion, we see that the central limit theorem is crucial in simplifying statistical analysis, making it possible to apply normal distribution techniques even when dealing with non-normal data. It finds wide application in fields like hypothesis testing, quality control, finance, and polling, making it indispensable for data-driven decision-making. The worked example of estimating the probability of a sample mean of cookie weight illustrates how the central limit theorem can be applied in real-world scenarios, even when dealing with complex distributions. So with this, we come to the end of this video. If you have not subscribed to this channel, you'll surely want to do that so you get to enjoy this kind of great content. And of course, you want to hit the notification bell so you can always get alerted when a new video is released. Of course, don't forget to comment, like, and share as we learn together from time to time. Until see you next time. Bye.